Hello, John Crooks here with the first in a series of presentations on pitch and pitch systems in music. Over the course of these presentations, we will get a solid definition of sound and frequency and understand how frequencies are turned into systems of pitch that we hear and use in music every day. This first presentation will be concerned with our basic definitions of sound, sound wave, and frequency. We will make a comparison between the audible spectrum and the visual spectrum and get ready to understand how the audible spectrum is subdivided into a pitch system. So without any further ado, I will turn it over to our first presentation. Our topic for today is pitch and pitch systems, frequency, the audible spectrum, and how we organize pitches. First, let's get a basic definition. What is sound? We can define sound as waves within a certain range of frequencies that can be perceived by the human ear. For our purposes, let's define wave as a transfer of energy causing matter, fluid, or solid to deviate from equilibrium, and frequency as the number of repetitions of an event in a given period of time. In the real world, sound waves are always complicated. For description and analysis, we use simplified waves. And this is an important thing to remember. When we're listening to sound in the natural world or musical instruments or speech, the sound waves are complicated both by the sound pressure in the room, the air around us that is moving and eddying, and the reflection of sound waves off of surfaces. This means that the analysis of sounds in the actual world is highly complex. To get a basic understanding of what a frequency is and what a sound wave is, we can use this simplified wave to describe phenomenon. So we see here a simplified wave. It's kind of a sine wave going up and down. And to get a basic understanding of sound, you can take your hand and wave it right by your ear, and you'll see that the air is being displaced by your hand, and a transfer of energy is causing the matter, the fluid, which is the air around our heads, to deviate from equilibrium, and the frequency of that event is the buffeting sound we can hear as we wave our hand by our ear. So here we have a simplified view of a standing wave, which is the kind of sound wave made by many instruments. String instruments, pianos, guitars make this kind of standing wave. And what happens when an instrument makes a wave like this is that the sound waves propagate, which means that their effect spreads in every direction. Now, sometimes sound does not spread evenly in every direction, but for our purposes, it can be described as a phenomenon just like we see here, where the initial impact of the sound wave spreads throughout the air around us evenly in every direction. This propagation causes changes in air pressure that are turned into chemical impulses by the inner ear, resulting in the perception of sound. So our ears and brains are doing some pretty sophisticated stuff with the changes in air pressure that enter our ears. Imagine what it is like in the real world when we take a sound wave like we see here that is complicated by reflection from walls and the individual timbre of instruments, for example, how much work our ears and brains have to do to really turn this into decodifiable data. Let's talk a little bit more about frequency and do some definitions. Frequency is measured in hertz, which can be abbreviated as Hz. The standing wave here has a frequency of 0.5 hertz. It completes one repetition or cycle of its pattern every 2 seconds. And to be specific, a cycle is what a wave does when it deviates from its equilibrium, in this case being a straight line, all the way in one direction, then back to equilibrium, back in another direction, and then back to equilibrium again. So this is doing that kind of a complete cycle every 2 seconds. This wave has a frequency of 1 hertz. It completes one repetition or cycle of its pattern every second. So we see here two frequencies, one of 0.5 hertz and one of 1 hertz. And the 1 hertz is twice as fast. For a wave to be audible sound, it has to be in the range of about 20 to 20,000 hertz. And this is a general range. Most people hear somewhere within this range rather than all the way down to 20 and all the way up to 20,000. But it's a good set of round numbers for us to use to describe the audible frequency range. Now, pitch is the location of an audible wave in the range of human hearing. And often when we're talking about musical instruments, we talk about pitches. For example, with this piano, my lowest pitch has a frequency of about 27 hertz, whereas the highest pitch has a frequency of about 4,186 hertz. A pitch system, which is what we have with Western tonal music and the tonal organization of other cultures, are organized ways of expressing this location, ways of expressing the location of a pitch within the range of human hearing. Hertz is one way to express a pitch system. Pitches with a low frequency in hertz are low, like this 27 hertz. And high pitches that we define as high have a high frequency in hertz, like that 4,186. Music notation is another way to express a pitch system. Pitches are placed relative to each other on a staff, with lower pitches being lower down on a staff and higher ones being higher up. So now we have some basic usable definitions for sound, wave, and frequency. Now we're going to make a comparison between the audible spectrum and the visual spectrum towards understanding how we organize pitches in our ear. So for this next section, we will spend a few minutes comparing and contrasting the audio spectrum, the range of frequencies that we can hear, and the visual spectrum, the range of light wavelengths that we can see. Obviously, hearing and vision are two completely different senses, but looking at how we parse the visible spectrum can give us some insight into how we organize pitches and frequencies in systems for music. So let's take a look. So here's the second part of our presentation on pitch and pitch systems, frequency, the audible spectrum, and how we organize pitches. Pitch as a spectrum. One way to think of the audible frequency range is as a spectrum, and we're used to hearing this term spectrum relating to our color sense. But when we're talking about music, people will often talk about different instruments having a certain pitch color, or a timbre can be equated with a color, and also certain groupings of pitches are described as having a color. Also, our system of 12 tones is referred to as the chromatic scale, and note that the root of that term is chroma, which means color. So let's take a minute to look at the visible spectrum. Here is the range of colors that we see, and as we can see here, the spectrum of visible light has frequencies from about 380 to 750 terahertz. Obviously, these numbers are much bigger than those we find in the audible frequency range. Let's take a minute and note the ratio. 750 to 380 is just about 2 to 1. So the ratio of highest to lowest frequencies in the visible spectrum is 2 to 1. Let's compare this to the audible spectrum. A very low sound like an avalanche is around 20 hertz or lower, and some people can hear that low. Bat sonar can be 20,000 hertz or a little bit less or quite a bit more, and some people can hear those very high sounds. So the spectrum of audible sound has frequencies from about 20 to 20,000 hertz. Note the ratio here, 20,000 to 20 is 1,000 to 1. So although the numbers are much lower in the audible spectrum, the ratio of highest to lowest frequencies in the audible spectrum is 1,000 to 1, 500 times that of the visible spectrum. Also note that within this tremendous range, our ears are sensitive to changes as small as 3 or 4 hertz. Our hearing can discern changes in pitch as small as 0.02% of the total spectrum. This is especially true in the range of frequencies from about 1 or 2,000 to 3 or 4,000 hertz, which is where we hear a lot of our natural sounds and some of our speech as well. So how do we take this vast range and organize it into the pitch systems that we use in music? As we know, the ability to accurately interpret sound is very important for survival and social interaction. Natural sounds, language, and basic orientation all require an advanced ability to process pitch information. So now we know that using light, we see frequencies in a range that forms the ratio 2:1. But the audible spectrum presents a vastly larger range, 1,000 to 1. How can we organize this audible spectrum? It really is quite a problem. We can hear through such a range of frequencies that the organization of this range becomes a very difficult cognitive problem for us to overcome. So what can we use to manage this wide range in musical pitch systems, for example? Well, the answer is the octave, which is a term we're probably familiar with. Using light, we see frequencies in a range that forms the ratio 2:1. What happens when we apply that ratio to audible frequencies? We can use an oscilloscope to find out. So that's exactly what we'll do for our next presentation. We will use an oscilloscope, which is a mechanism we can use to visualize waveforms, to understand a little bit more about what the octave is, how it behaves in terms of actual wave forms, and how the octave can be used to organize a musical pitch system. In this first episode, we have learned our basic definitions for frequency, for sound, and for sound wave. We have seen some simplified waves in action and made some parallels between the audible spectrum, where we see through a very wide range of frequencies, and the visible spectrum, where we see through just a 2:1 ratio of light frequencies. So thanks very much for tuning in, and click on episode 2.